Hi guys, let's do some revision questions on the binomial distribution and see if we can't knock them over and gain some more knowledge of this topic as a whole, okay? So, without any further ado, let's get going. In order to assess the quality of computer games being produced, the manufacturer selects 10 games at random before they are put into boxes for delivery to shops and inspects them, okay? Now, question 1. If it is known that 8% of games are defective, find correct to 4 decimal places all of these things. Alright, well, we'll just do them one by one. Now, it looks to me like this is a binomial situation because we've either got defective or not defective. The probability is always the same and the events are independent. So, no problem. Let's go at it with that in mind. So, part 1, let's have a look at that. Now, I always start off with this statement because I like to be grounded and I like to know what my random variable is. Otherwise, you can just get a woolly thinking syndrome with this stuff and you really don't know where you are. So I start off, let capital X be the number of defective games. So what are we doing? If it is known that 8% of games are defective, find correct to 4 decimal places the probability that one of the games in the sample will be defective. Well, come on, you pause the video now and don't let me do it and just show you. You need to exercise your brain. So you try all these on this screen and you come back to me when you're ready, okay? See you soon. Okay, you're back? Alright, so what we would do there is we'd say n equals 10, the sample size or the number of trials equals 10, p equals 0.08, which is the probability of getting a defective game, and we know that the probability that x equals 1 is 10c1 times 0.08 to the 1 times 0.92 to the 9 in accordance with our binomial formula that we've all learned, and that comes to that, and that comes to 0.3777 to 4 decimal places. Please go back and read the question before you leave it and put a box around it like I do so that the examiner can see what you're doing. Okay, so that's 1, well and truly done. Now, question 2, the probability that at least one of the games in the sample will be defective. Okay, well, that's pretty easy. So all we need to do there, what I would do is I'd work out the probability of 0 games and I'd take that away from 1. Okay, so that comes to that's 0 games. Therefore, the probability that we have at least 1, which is everything else after all, apart from 0 games, would be 1 minus 0.4344, which would be 0.5656. How did you go? Did you get that? Well, jolly good upon you if you did, okay? And if you didn't, well, just have a think about it. Okay, question 3. The probability that exactly one of the games in the sample will be defective given that at least one of the games is defective. Well, that's a conditional probability situation. You know how to do that, don't you? Well, here it comes. The probability that x equals 1 given that we know that x is greater than or equal to 1 would be the probability of, this is just your multiplication formula, okay, for probability, okay? So this is the probability that x equals 1 and x is greater than or equal to 1 over the probability that x is greater than or equal to 1, okay? If you don't know that formula, please go back to your textbook and have a look at it. It's called the multiplication rule of probability, okay? Now we can work that out very easily because we just worked out the numerator in part 1 and the denominator in part 2. This one here is the numerator, this one here is the denominator, and we get that, so we can work that out, Okay, there's our answer. Now, let's move on. Part 4, the expected number of defective games in the sample. Well, that just means the mean or the average for a binomial distribution, and you know the formula for that, don't you? I hope so. It's NP. NP. N is 10, P is 0.08, and therefore we get that 0.8. Okay, that's the expected number of defective games in the sample of 10. Alright, number 5, to keep us alive, the standard deviation. Alright, standard deviation means you have to work out the variance, and the variance with a binomial distribution is just is NPQ or NP into bracket 1 minus P, same thing. Okay, some people refer to 1 minus P as Q. Very easy, very, very easy. So we'll just do that. Plug and chug. and we get that, and we get this, and then when we take the square root of that, remember we're doing standard deviation, guys, that's the variance. We take the square root of that and we get that to 4 decimal places and everything's good. We've done the job and we've got all of the marks. We've got full marks and we're patting ourselves on the back, okay? Excellent. Let's have a look at this one. Now, it is found that after a new machine is installed, that the probability that exactly one of the games in a sample of size 10 being defective, given that at least one of the games is defective, is 0.56. What proportion of defective games is now being produced? Okay, and we want the answer to 4 decimal places. Well, this is an interesting situation where they're actually, I think we have to go backwards. We have to go backwards from the multiplication rule to work out an unknown value of p. Okay? This shouldn't be a problem. And if we're doing it to 4 decimal places, we're allowed to use the CAS, guys. Goody, goody. So, okay, this is our multiplication rule. We're looking for we know that the probability that x equals 1 given that it's greater than or equal to 1 is this, according to this formula. And if we simplify that a little bit, we can just express that numerator as that, because the left-hand side is in fact more restrictive than the right-hand side, so it covers both situations. If you think about that, if x is 1, well, it certainly is automatically greater than or equal to 1, isn't it? That's a less restrictive constraint. This one's the one which covers both, okay? So now, let's just flesh that out a little bit more. So we know that 0.56 is equal to this over this, because that's 1 minus the probability that x equals 0, isn't it? Yeah? Okay, now, we're going to let the probability of a defective game, we'll let that equal to p, because we have to find that out, okay? And now we're going to work out what is the numerator. Well, it's that, 10c1 p to the 1 minus p to the 9, and that's that, because 10c1 is just 10. Now, the denominator is that, yes, which is equal to that, which simplifies. That's just 1. nc0, no matter what the n is always 1, okay? It's always 1. And anything to the 0 is 1, so that line simplifies to that. So we can rewrite the whole thing now like that. 0.56 equals that, and we really want to solve that on the CAS because we're allowed to do it to 4 decimal places for p. So I've actually just massaged it a little bit more, but then I thought, oh, yes, but now I'm just going to go for the CAS. So I probably didn't need to do those 2 lines there. You could just go straight for the CAS at this point here, guys, to save yourself a bit of trouble. And that's what I got. That's what I got. Now, p is 0 makes absolutely no contextual sense at all, okay? Because of this, the data we've got here. It makes mathematical sense as a solution to that situation there or that situation there, but it makes no contextual sense in the situation in which we are dealing with these probabilities and these defective games, all right? Now, so therefore, this has got to be the one we're going to use. P is 0.1100 to 4 decimal places, and therefore that's our answer, okay? Very excellent. Now, this one here, let's go for this now and see what we can make of it. We've got pieces of waste paper each being crumpled and shaped into a ball shape and are being thrown across the room, hopefully not in my classroom, aimed at the waste paper bin. There's a 50% chance that each of them is going to go into the bin, alright? So this is binomial, sticking out a mile, binomial. So both with and without technology, well, that's very interesting. With and without technology, find how many attempts are required in order to achieve a better than 0.95 probability that at least one will go into the bin. Well, that's very interesting. This is a case where we've got to work out what the number of trials are. These are always a bit of a trial to work out too, by the way. This is the most difficult stuff you're likely to have thrown at you in binomial, okay? That's why I gave you a question on it. So part A, let's do it without technology. Come on, let's grit our teeth and charge onwards. Now, yes, I always start off with my little grounding statement there, which grounds me and gets me to realise what I'm doing. Let X be the number of successful throws across the room, hopefully not in my classroom. We've got okay, the probability that x equals 0, see, I'm coming at about this in the reverse way again, because if we want at least 1, I'm going to take the probability of 0 away from 1, okay? So the probability that x equals 0 is nc 0, 0.5 to the 0, 0.5 to the n, and hence, guys, well, that comes to a half to the n, right? Hence, the probability that x is greater than or equal to 1 will be 1 minus that. Yes? Very, very simple. Okay? So we can do this with a little equation set up. We don't have to do it completely by trial and error. Now, all right, let's keep going with that. We're saying that that is going to be greater than 0.95, better than a 0.95 probability. Okay, so what we've got to do is find the value of n, which fits this inequation, don't we? We do. So therefore, I'm just massaging a little bit now. I've taken 1 away from both sides, and now that's very important. I've multiplied both sides by -1, and I've reversed the little inequality sign. Here I call it the crocodile mouth. I've reversed the direction of the crocodile mouth. Please don't forget to do that. That's the biggest booby trap of all in inequations, guys. Alright, how did I do that? How did I do it? Well, I changed it to that, right? Because 0.05 is 1 over 20, and a half to the n is 1 over 2 to the n. So I've got to basically deal with this now, okay? So 1 over 2 to the n is less than 1 over 20th. Now, if I care to flip that, because I've only got one term on either side of the inequation, that means that this means, again, that 2 to the n must be bigger than 20. Now, you think about that, okay? If this fraction here is less than that, that means this number's got to be bigger than that number to make the fraction, if that's on the denominator, to make the fraction here less than the fraction there. Do you understand? That's got to be bigger than that to make the fraction smaller, because when the denominator gets bigger on a fraction, the fraction gets smaller. So, right, there's a little bit of thinking involved in this, yes? And that's a really good thing for you to do, okay? Now, this is really easy now. If we've got 2 to the n is greater than 20, think about it. What's 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 3 is 8, 2 to the 4 is 16, 2 to the 5 is 32. Ooh, there it is. Okay? So, n has to be an integer, of course, because this is the number of throws across the room. You can't have half a throw, or a fraction of a throw. So therefore we know that there we've got that. 2 to the 4 is 16, which is less than 20, and 2 to the 5 is 32, which is more than 20, so therefore the answer must be 5 attempts needed. Okay? And that was all without technology. You see, aren't you proud of yourself? I'm very proud of you. And therefore, we're going to now do the thing with technology, which is an absolute snap, of course. There we go. Badumch. We've got solve 1 minus a half to the x is greater than 0.95. We're solving it for x. We hit the enter key and we get that. But of course, x can't be that. X is aka n in our case. But of course, you can't have 4.3 throws. That's ridiculous. So you work it out for both to make sure you know what you're doing. Okay, you work it out for each numeral, each integer either side of that decimal number, for 4 and for 5. Always do that, because you know, if you're in an exam setting, you're a little bit stressed, you may not be thinking as clearly as you need to, so just let the CAS do the work for you guys. So this one here is less than 0.95 probability. This one here is more, and of course that's the one we want. Alright? Fantastic. Okay, so 5 attempts needed. Alright? Great work. Now this one here, repeat question A if the probability of getting the paper into the bin is exactly 1/3. Now guys, I'm here to tell you this is considerably more difficult without technology. So why don't you have a go? Pause the video and come back to me when you're ready, okay? But just, you know, gird your loins and just think. Get that wonderful brain of yours thinking about what you're doing in order to enable you to do this without technology, okay? See you soon. Okay, you're back. Without technology, let's go for it. So we're saying that the probability that x equals 0, as we did last time, except with 1/3 inserted in here, would be this thingy here on the right-hand side. Yes, that's correct, isn't it? Which simplifies to that. Alright? So therefore the probability that x is greater than or equal to 1 is going to be 1 minus 2/3 to the n. Okay, so that is our inequation that we have to solve for n. Okay? Alright. Did you get that far? Well, good on you if you did. And just keep going if you didn't. See if you can get it from here, okay? Along with me. Now, what would you do next? Well, looking at that, I think I'll subtract 1 from both sides. That's probably the easiest thing to do at this point. Now, we probably should multiply both sides by -1 and make it just a little bit more civilized and reverse the direction of the crocodile mouth at the same time. Please don't forget that one. That's vitally important. Okay? Very good. Now, it's a little bit challenging, guys. I think I'll change that 0.05 into 1/20 and then see what to do with that beast. Well, what are we going to do with this horror? Okay? Well, let's try. Let's try. We'll just do trial and error, okay? Try n is 7. That must have been the first number that came to mind. So, what do we get? 2/3 to the... I told you it was difficult, didn't I? But don't worry. Come on, you can do it. 2/3 to the 7. Well, 2 to the 7 is 128, in case you want to multiply that out. 3 to the 7, and you can do that with long multiplication. Come on, you definitely can. I did it, so can you. That's 2187. Well, now, you think to yourself, goodness gracious, is that is that less than 1/20th, or is it not? Well, come on, you just multiply this by 20. You see, and see what you get. So you got 20 times 128, and yes, you can do that without technology, with your pen and paper and your brain. You can get 2560. Okay. So if that number there was 2560, you'd have exactly 1/20th. But that's less. That's less than 2560, and therefore the fraction must be more than 1/20th. So we want less, don't we? You see? So we better try something else. Oh, groan. But we'll do the same procedure, okay? Try n equals 8, and what do we get there? Now, you can do it. You can do it. I know you can. I did it this way. 2 to the 8 is 4 to the 4, and 3 to the 8 is 9 to the 4. So that's 81 to the 2 for the denominator and 16 squared. Now, you can do that on a piece of paper. Come on, you can long multiply. If you can't, you better hurry up and get good at it, okay? You get that. Now, what's 20 times this beast? Let's work that out. 5120, and 5120 is less than 6561, okay? So therefore, we must have 2/3 to the 8 must be less than 1/20, okay? Which is exactly what we want. Therefore, we know that we need 8 attempts, okay? Now, I know that was difficult, but look, you've got to get good at using your head without CAS if you need to, and that was the purpose of me giving you this more difficult tech-free question. Now we'll do it with the technology, and it's a snap, absolute snap. So you're solving for 2/3 to the x, aka n, is less than 1/20. If we're solving it for x, we get x is greater than that. Now you've got to try 7, and you've got to try 8 to see what the probability comes out to be, alright? So this here gets you, righto, that gets you 0.0585. This one gets you 0.0390, and it had to be less than 0.05, right? That's 1/20th, less than 0.05. This one is the one that gets the Guernsey, guys. This was the right one. Therefore, we can say that we need 8 attempts, yeah? Excellento. Excellento. Now, okay, what have we got here? We've got part C, and then we've got part D, finishing off with a big bang. Right, let's read this. Use technology, okay, thank goodness, to find the number of attempts required to achieve a better than 99% success rate of getting at least 2 into the bin if the probability of getting the paper into the bin is exactly 1/3. Well, it's a similar sort of thing, isn't it? But except that we're looking at the number to get at least 2 into the bin, whereas before it was at least 1, wasn't it? So it's a little bit more complicated again. So let's just get our ducks in a row. P is 1/3. N is what we have to find out, okay? So we need the probability of x being greater than or equal to 2 to be more than 0.99. Now, is that what that says? I think that's what it does say. It's better than 99% success rate of getting at least 2 into the bin. Yes, that's right. Okay, so therefore we want the probability of x being equal to 0 or x being equal to 1 to be less than or equal to 0.01. That's going at it in reverse, okay? Now let's try and flesh that out a bit. We get, okay, this is the 0 bit, this is the 1 bit, okay? So NC0, 1/3 to the 0, 2/3 to the n, plus NC1, 1/3 to the 1, 2/3 to the n minus 1 is less than or equal to 0.01. It looks ghastly, doesn't it? But come on, let's forge onwards. Now, this is very much simpler than the previous line. That just gets you, that of course is 1, that's 1. So we get 2/3 to the n, plus now this is going to be NC1 is just n, times 1/3, so n over 3, times 2/3 to the n minus 1 is less than or equal to 0.01. Okay, that's where I think where we dive for the CAS, okay? Solve for CAS for the equality, guys, not for the inequation above, because the TI handheld CAS device, which is what we use in our school, will not solve for this beastly thing. It'll just solve for the equation, okay? If your CAS handheld device will solve for that, well, jolly good upon you, you go ahead and do it, but ours doesn't. It only solves for the equation. And then we'll test each integer either side of whatever answer we get to work out which one is the one we require, okay? Which value of n is the integer value that we require, satisfying this inequation here, okay? Alright, let's go. So we go solve for this plus this equals 0.01 for x, and x is really n, but I usually use x when I'm using the CAS device. We get this. Well, of course, look, this makes no sense. How can we have a negative number of throws? That's ridiculous in the context of the situation we're dealing with, although it does make mathematical sense in solving this thing. So we get 16.89 and all that. Now, what we've got to do, guys, is check the value that we get for, see, we test this equation here with a value of 16, and we test it again for a value of 17, and we see what value we get from plugging into the left-hand side of this, okay? Now, we've got to basically, remember we were really trying to solve for less than or equal to 0.01. Now, if we put 16 into the left-hand side here, we get more than 0.01, so that's no good. And then we put in here, for x is 17, we get the value, less than 0.01. So that's the one that we want. 17 attempts needed, okay? 17 attempts needed to get at least 2 into the bin when the probability of getting it in on any one throw was 1/3. That's the deal. Okay, here comes the grand finale now. This is, have a look at this. Pause the video, have a go, okay, and come back when you're ready, okay? Alright, you're back. Using technology to find the number of attempts required to achieve a better than 99% chance of throwing at least 50, my goodness, successfully into the bin if the probability of getting each one into the bin is exactly 1/4. Wow. Now, this is a case where there's just no way, Jose, that you can come up with an equation that's going to work on the CAS device. It just isn't going to work. At least 50? Come on. You know, how do we do that in an equation? The equation would be like, 10 kilometres long. So we can't do it that way, okay? So, we use technology using what's called a table of values. Okay, that's the best way to do it, all right? Now, so first of all, we define, on my TI CAS handheld device, I use the binomial cumulative distribution function with a parameter of n trials, or x trials, with a 0.25 probability of success, with a lower limit of 50 and an upper limit of x, aka n for the n trials, if you like. Okay, but I just use x as I was explaining before, and we put that in as a function on the calculator screen. Okay, in the TI CAS handheld device thingy, and that's the first thing we do, right? So there it goes. Okay, I put that in, and there, and then I've defined it as f1 of x. Okay, so that's all done, squared away. Check, check, and check-a-rooney. Now, what we then do is we add a lists and spreadsheets to the calculator ensemble of little thingies that we can do, a separate screen, and then we convert that to a table of values. Okay, now if you've got a Casio or some other handheld device, you've just got to translate that into whatever you need to do. Okay, but on the TI, you set up the table by choosing, when you're in the list and spreadsheets screen, you choose f1 of x, and then you edit the table of settings to start at x equals 50 and step upwards by 1. Okay, and then you find the first entry for which the cumulative probability is greater than 0.99, which is what we're supposed to do up here. So we're scrolling down the screen, we're trying to find the value of x, aka n, or the number of trials required to get a better than 0.99 probability on the list, on the screen, okay, of getting at least 50 in the bin. Okay, this must have been a very troubling day for whatever they were working on. 50 into the bin. So, all right, let's go and see what we get. Now, if you have a look, I've scrolled down the screen, and you can see that I've got the binomial CDF function in here, into the thing. These are my values of x, or n. Okay, and I've got to get more than 0.99. So which one? Yes, that's 250 odd attempts, 260 attempts. Now, we're nearly at 0.9. Oh, look. Look. See, 261, we're still under 0.99. 262, we're just above. So, guys, 262 attempts. What a waste of paper. And that's what we need to have at least a 0.99 probability of getting at least 50 in the bin, when the probability of each individual one getting into the bin is 1/4. That's the answer. And I hope you had as much fun as I did bringing this to you. And please, just onward, keep practicing and get good at them, and you'll be an expert before you know it. And I'll see you soon.